Let me start recording and share screen. All right, does this look okay?
Yeah.
All right, so let me get started. Okay, sorry that I don't not feeling well. I'm gonna have to give this lecture online, but hopefully it will be all right for most of you. And it's recorded, so I see rather few of you today, but you know the other students can watch it online later. So let us jump into the time-dependent perturbation theory again. And just to review what we have done on Wednesday, so we looked at this expansion of the time evolution operator in the interaction picture. The 0th order is just 1. First order is what we use for the usual Fermi's golden rule. And today we're going to use the 2nd order piece, which has 2 powers of the interactions in it. And we also looked at this the expression by inserting the complete set of states between 2 interaction Hamiltonians. And by doing this time integral, we came up with the last expression down here. And in the end, by doing this integral over time, we have obtained the last expression down here. So the initial state would have the first interaction going into intermediate state. An intermediate state propagates using this energy denominator. And then the intermediate state would go over to the final state by the 2nd interaction Hamiltonian. So that's the expression we are going to use for practical calculations. We also introduced this mathematical trick to damp all the terms in the limit where the time interval is tend to infinity by putting this epsilon factor in it. And so that would take care of this last factor we don't need. And that as a result, we have this I epsilon in the denominator. And I told you already that this actually has to do with this idea of the resonance scattering, and that will come up later, hopefully today. So this is the expression we're going to use for actual calculations. And I also introduced the idea for the Feynman diagrams. So the first order piece, which we did use already in the decay rate of from 2p to 1s, and you're actually working on a homework problem right now. And this can be depicted by this diagram of the initial state coming in. You have this interaction Hamiltonian V, and then that immediately takes you to the final state F. On the other hand, the 2nd order perturbation theory will give you this piece, that interaction, the initial state I would hit this interaction V and becomes the intermediate state M. And the intermediate state propagates from initial time, let's say T1 to T2. And this propagation of the intermediate state is described by this propagator or energy denominator. And then after this propagation of the intermediate state M, the M hits this interaction Hamiltonian V so that it will go over to the final state F. So this is just a convenient way of drawing diagrams so that we can remember what expression you're going to use in actual matrix element calculation. So after doing this time-dependent perturbation theory and integrate over time, in the end, the only thing you need to remember to perform the perturbation theory at any orders you like is these diagrams. So you have some initial state, you have some interaction Hamiltonian, then you just go through various stages of this intermediate states. And every time you have intermediate state, you have this energy denominator as a way of propagating one intermediate state from one time slice Ti to the next time slice Ti plus 1. And that's the way you can compute the matrix elements. And for our purposes, the interaction Hamiltonian was an expansion of this point particle, the 1/2m p minus Ea squared. So we have already used this piece, p dot a, for when we actually do this first order perturbation theory for the 2p state decay into 1s. But for the scattering of the photon of an atom, we need to go to the 2nd order perturbation theory. So we need these pieces done twice. But also at the same time, we need to use the last term once so that you can absorb one photon, you annihilate it, and create a photon to the final state. So we end up using the last term once in this first order perturbation theory, or the first two terms twice to get the final process. So that's how we are going to actually talk about this. So before getting to the scattering of a photon of an atom, this is just a review of this 2s state decay into 1s. And what we did already talk about is that when 2s state decays to 1s, there was no matrix element using the usual dipole approximation. So namely that using these first two terms in the interaction Hamiltonian once, there was no matrix element for this. So as a result, we have to go to the second order perturbation theory by emitting two photons instead of one photon. So the way you can do this is that using this first piece, P dot A, or A dot P is the same thing in Coulomb gauge. And so I use this first two terms in this first, the first stage of initial state going to the intermediate state. And intermediate state may be 2p state as an example. So by using this the P dot A term, the A contains the creation operator of the photon. So you can create one photon using this operator. So intermediate state then would be 2p state plus one photon. And 2p state plus one photon has a different energy higher than 2s state because you have emitted a one photon already. So EM is bigger than EI. So this energy denominator doesn't vanish, which is good. And then you use the same operator P dot A once again, so that 2p state then goes all the way to the 1s state by emitting yet another photon, because P dot A again contains the creation operator for the photon. So the final state would be 1s state plus two photons. So that's one way you can get this matrix element. And as you can see immediately, this intermediate state doesn't have to be 2p state. It could be 3p state as well, or 4p state. So within a dipole approximation, you are supposed to sum over all the p states of the atoms. And in principle, you can also sum over the continuum state as well. It doesn't need to be a bound state either. So after summing over all of those states, you complete the second order perturbation theory in this expression. And there's also a contribution to the matrix element by using the last term in the interaction Hamiltonian, EA squared. So A squared, each A contains the creation operator for the photon. So the A squared, vector potential squared, then contains two powers of the creation operator. So using this term once inside this expression, FVI, then you can go immediately from 1s state, and V creates two photons. So the initial state is 2s, and you create two photons with V going to the final state of 1s state plus two photons. So you need to sum all of these things up. So that's the way you can get this the contribution of a 2s state decaying to 1s state plus emitting two photons. Okay, any questions about this slide?
For when you go from like the 2s state to the 4p state, that's like a gain in energy. So I'm not sure how you're emitting two photons.
Yeah, so the idea,
sense?
So the idea is that the I is the 2s state, right? And the V emits one photon and go to some intermediate state. But if 2s state goes to 4p state, of course, energy is a lot higher. So the intermediate state then has 4p state plus one photon. So you have to pay the price of going to the higher energy state with the hydrogen atom plus emitting a photon. So EM is a lot higher than EI. But that's okay. So this is actually an idea of the quantum mechanics allowing you to borrow energy within a certain principle. Intermediate state has a lot higher energy than the initial state. So delta E is pretty big. But as long as you pay the energy back within delta T given by H bar over delta E, that's okay. So you can borrow as much energy as you need to make the the matrix element non-vanishing, and as long as this doesn't take much time within the delta t given by h bar over delta e. Am I answering the question, Emma?
Yeah, that makes sense.
Okay, good, good. Any other questions? Okay, and so I did talk about this idea before, and then you can go ahead and do the calculations of this. And I'm not going to actually perform all the calculations for this purpose, but I just give you how the estimates go. So the energy denominator has this suppression by the energy. This factor is actually coming from the normalization of the photon, the expansion of the vector potential in terms of creation annihilation operator. So that gives you a factor of alpha -2 because the energy goes like that. And you also have the phase space for the final state photon, and energy delta function will cancel the radial part of this integral, but the other pieces remain. So you have q squared d omega for the phase space integral, and q squared, each q is basically energy of the photon. Energy of the photon goes like alpha squared, and so this actually gives you alpha to the fourth. And then remaining matrix elements actually goes like this. This is the same calculation we have done with the dipole approximation. So the V contains P in it, and P can be written as the commutator between Hamiltonian and X. And the Hamiltonian piece extracts this energy difference between the initial state and final states, the intermediate state in this case, and the rest is X. And so the energy difference is actually alpha squared, because the energy levels go like alpha squared, and X is basically the Bohr radius. That's 1 over alpha, and by putting them together, I get a contribution like alpha cube. So at the end of the day, the entire expression goes like alpha to the fifth, and this is actually extremely suppressed. Sorry, this is actually I missed this up. So clearly I've jet lagged. So anyway, so that's the way I can compute the decay rate for the 2p state going to 1s state, and this is the way I was trying to review the 2p to 1s calculations. But now I apply this to this 2s plus 1s, so I get this 2 photon emission. So that's why this normalization factor from the mode expansion of the vector potential appears twice instead of once. That already gives me alpha to the -4th. Now looking at this, the contribution to the intermediate state, I have this energy denominator in a matrix element twice. And one matrix element was actually given by this alpha cube, as we talked about for the 2p to 1s state. So you actually need to combine them twice. And you also need to count this energy denominator. So I get the alpha cube twice, that's alpha to the 6th. Energy denominator is alpha squared, and that gets squared, so that's alpha to the 4th. So that's how I get alpha 6 over alpha to the 4th, and end result is alpha squared. And I also need to do the phase space integral for 2 photons. And in the case of 1 photon, I had this alpha to the 4th. And in the case of 2 photons, each of them gives me alpha to the 4th. That gives me alpha to the 8th. And even with this energy conservation, one of the radial integral still remains, and that would give me another factor of energy, that's alpha squared. So that's in the end, this phase space integral ends up giving me alpha to the 10th. So if you put all of them together, so this 2s to 1s emission it goes like alpha to the 8th. So you have 3 additional powers of alpha in the decay rate, and that's how this 2s to 1s decay is suppressed by something like a 6 orders of magnitude compared to the usual dipole emission of the 2p to 1s state. So you have to go through more detailed calculation in this, but in the end, the hydrogen atom of 2s state decaying to 1s state with 2 photon emission has the lifetime of the order of a second compared to a nanosecond of the 2p decay. So that's why 2s state is metastable. It's not stable, it eventually does decay, but it can hang on for a long time on atomic scale, So for typical decay rates of nanosecond, this is enhanced by almost 9 orders of magnitude. So that's the decay rate of 2s. And I already showed these numbers before. So as far as I looked, and if you can find actually the data on this, let me know. So as far as I looked, in the case of hydrogen atom, lifetime was too long to be measured experimentally. So the only thing I could find was sort of hydrogen-like atoms, for example, helium. And when you have the helium, well, the first ionized helium, then you have this helium nucleus with a Z equal 2 and only one electron orbiting around it. So the calculation would be basically the same as the hydrogen atom, but the everything is enhanced by Z equals 2. And so lifetime becomes correspondingly shorter. So this is the decay rate per second. So compared to the hydrogen atom of the decay rate of 8 per second, helium would have a faster decay rate of 500 per second. And this had been measured experimentally, and the theoretical calculation and experiment really do agree. And the similar, the measurement had been done with the highly ionized atoms of the larger Z, like oxygen. And in the case of oxygen, obviously you have 8 electrons normally, but you have the 7 electrons ionized, so that you have only 1 electron left. Then the system again is hydrogen-like with Z of 7 instead. And then of course decay rate is much faster because of that. So the theory calculation tells you is 2 million per second. And experimental measurements also show 2 million per second, and so forth for even bigger atoms. So the theory and experiments agree, but based on this idea that you go through the second order perturbation theory with a 2-photon emission instead of 1-photon emission. Okay, I heard, maybe was it Kate's voice?
Yes, yes.
Go ahead.
I have a question. Can you go back to the previous slide?
Mm-hmm.
May I ask, what is the quantity, like because I don't understand the units for the dimensions for the integral, like from 2p to 1s state, we have the integral of dq to the power of 3 over 2 pi h bar to the power of 3, 2 pi delta ei minus ef. I don't know what this quantity that we are calculating.
So okay. So in Fermi's golden rule, you have to sum over all final states, right? So in the case of 2p to 1s, you only keep this first order perturbation theory. You don't need to go through this intermediate state. And then what you have to do is sum over all possible final states, which includes all possible the final state of the photon. So final state is 1s state plus 1 photon, and you sum over all possible final states for the photon. So that includes this 3-dimensional integral over q, which is the momentum of the photon. And the Fermi's golden rule itself has this delta function. So that's how you end up with this kind of integral of the integral over q in 3 dimensions with the delta function. And for the dimensions, I'm not keeping track of the dimension here, so I'm ignoring all the dependencies on the electron mass. I'm only keeping track of the dependence on the fine structure constant on this slide. But in practice, you put in, for example, this E over M into the matrix element inside this first term, the FVI. So that gives me 1 power downstairs for the electron mass. And when you also compute the matrix element for the P over M, and then you have to convert this into this commutator between Hamiltonian and X. And then you have this power, the energy of the 2p and 1s appearing, and they are all given by alpha squared times mc squared of m being an electron mass. So there's another factor of electron mass there, and so on and so forth. So right now I'm not keeping track of the dependencies of electron mass, but if you actually work everything out, the gamma goes like alpha to the 5th times mc squared, which has the dimension of energy. So gamma has the dimension of energy, and together with h bar, that has a dimension of 1 over time. So that's how everything should work out. Did I answer your question? Okay.
Yeah.
Go ahead.
Thank
Go ahead. You're happy?
Yeah. Yeah.
Okay, good.
Yeah.
Okay, so that's the first example of the secondary perturbation theory. And now we go to this more interesting example of the photon scattering of an atom. So idea is that you have some hydrogen-like atom or whatever atom you like, and you send in a photon, and then the atom would scatter this photon in an off direction. And whenever you talk about the scattering process, you talk about the probability of the scattering expressed in terms of what is called the cross-section. So this is the rate of the reaction per unit flux of the photons coming in. And I don't know if you have actually studied cross-section in your quantum mechanics class. Can anybody speak up?
Yes, we did.
You did? So typically in quantum mechanics, what you talk about is that you have some potential, you send in a particle, and you interact with this potential, and particle gets scattered off this potential. So now we are talking about something a little bit more realistic in a sense that you have actually an atom, you send in a photon, and photon would interact with the electron inside the atom, and photon gets scattered in off direction. So to get this idea of the cross-section, which apparently you study in quantum mechanics, so maybe I don't need to dwell too much time on this, the cross-section being a cross-section has a dimension of the cross-section, namely the area or length squared. And the reason why this quantity has this the dimension of the length squared or area is that the rate, of course, has a dimension of 1 per time, just like what we discussed for the 2p state decaying to 1s state. But the flux of the photons has a dimension of length inverse squared and inverse time. And the idea is that you have the bunch of photons coming in, and then the bunch of photons is contained inside a volume, and the volume has, of course, 1 over L minus cube, but they come in with a some velocity, which has a dimension of LT inverse. So if you combine them together, the flux has this dimension of L2 minus 2 T inverse. So that's basically L to the minus 3, the number of photons inside this box, times its velocity, LT inverse, and the product of that has this dimension of L2 minus 2 T inverse. And so that's this expression over here, where the certain number of photons inside this volume, 1 over L cubed, times the velocity of the photon, of course, which is the speed of light. And so as a result, the cross-section can be expressed by the idea of the Fermi's golden rule. So the pieces from 1 over h bar and beyond is the usual Fermi's golden rule that has a dimension of rate, 1 per time. Then you sum over all the final states of the photon. So that's this big sigma over here. And then you divide it by the flux factor. So you multiply this rate by L cubed over C. And the end result is a quantity that has the dimension of the area or the cross-section. So very roughly speaking, this represents basically the size of the target. So imagine that you are doing darts and you're throwing your darts onto a target. And if the target is big, then you have a better chance of hitting it. If the target is small, you miss it pretty much all the time. So the probability of the hitting the target is proportional to the area of the target. So that's why this quantity of the cross-section, which has a dimension of the area, tells you the idea of how often you can hit the target, namely the probability of hitting it. So hence the scattering is always described in terms of the cross-section, which basically tells you the size of the target. So if the photon is throwing off to an atom in a random way, if the target is big, then the photon gets scattered with high probability. if the target is small, the photon doesn't hit the target very well. So you can describe the probability of the photon getting scattered by an atom using this quantity of the cross-section that has dimension of the area. Okay, any questions about this? Okay, so now we actually use this formula and start computing things. So once again, this is the formula for the scattering cross-section. And I now draw this the pictures in the opposite direction. Again, because of this Dirac's convention, the initial state is the ket vector on the right, and the final state is the bra vector on the left. So I'm following this flow of time from right to left, like in Arabic and Hebrew. That's why I actually inverted this the picture. So initial state is now drawn on the right, and the final state is drawn on the left. And the idea is still the same. I use this interaction Hamiltonian by expanding this a single particle Hamiltonian of 1/2m p minus EA squared. And p squared over 2m is part of the 0th order Hamiltonian. So I just leave that out. And interaction Hamiltonian is the rest. That's why I have this p dot a dot p, and the a squared. And I start using this Hamiltonian in this expression at the second order in perturbation theory. So each A contains either creation operator or annihilation operator of the photon. So we are talking about a scattering process here. So I need to annihilate initial state photon, and I need to create the final state photon. So for every A, I pick up the annihilation operator and creation operator in such a way that I keep first order in annihilation and first order in creation. And the way I can do this from this interaction Hamiltonian is that I can use the last term, which contains a squared in it, at the first order in interaction, namely this FBI matrix element. I put this EA squared into this. And because a squared can contain 1 power of annihilation operator and 1 power of the creation operator, I have a contribution that looks like this, again, in terms of the Feynman diagram. So the interaction Hamiltonian I insert here is E squared 2ma squared, where A is the vector potential. And I use 1 power over A for the annihilation of the photon. And I have the other A for the creation of the photon. And so that's this diagram. So initial state, maybe let's say oneness state of the hydrogen atom. Final state is also oneness state of the hydrogen atom. And then I have 1 photon coming in, 1 photon going out. And then this A squared would take care of this matrix element. So that's one way I can get a contribution to the matrix element. But I can go through also this intermediate state at a second order perturbation theory. I basically use P dot A twice. And one way of doing so is that first P dot A would annihilate the photon. And that goes through this intermediate state, which does not have a photon. And then the intermediate state would emit the photon by another factor of P dot A, going over to the final state. So that's one way I can use the second order perturbation theory to contribute to the scattering process. But there's another way. Instead of annihilating the photon with the first interaction, I can create a photon. So initial state has oneness state plus a photon, and then interaction would create yet another photon. So intermediate state then has some atomic state plus 2 photons. So if I draw a line at the intermediate time slice in this vertical line over here, then at this time slice, I have the photon which came in, still there. I have intermediate state of the atom and another photon that have been created. So this intermediate has 2 photons in it. And then the second Hamiltonian would then annihilate the initial state photon. So that takes care of the initial state photon gone now. But the other photon that have been created is still there. And so the final state would have this oneness state of the hydrogen atom plus the photon emitted. So this contribution I just talked about and the contribution I talked about just a minute ago are different because in the first example I talked about, intermediate state does not have any photon. In the contribution I just talked about, intermediate state has 2 photons. So there are 2 different contributions to the matrix element. So at the end of the day, I have the sum over all 3. The first one with this a squared term at the first order perturbation. So that takes care of the both annihilation of the first photon and creation of the second photon at the same time. In 2 contributions that go through this intermediate state, and the one contribution has no photon for the intermediate state, and the last contribution has 2 photons for the intermediate state, and you are supposed to sum all of them. So that's how you get this complete expression for the matrix element. So let me stop here again to see if there are any questions.
I have 2 questions.
Okay, go ahead, Kate.
So the first question is, I am still a bit confused with the. So we have gamma, and the gamma is in the form of what we have in the sigma term. So.
That's right. So except for this flux factor, that's right.
Yes. So the flux factor has the dimension of t squared over m, and the gamma should be having the decay rate where it is 1 over t.
Right.
And now I'm not sure because I don't know where the m go.
Let's see. Did you say L? So let me show this slide again. So cross section has dimension of area. The rate gamma from the Fermi's golden rule has dimension of 1 over t, and flux factor has this dimension of 1 per area per time, because it basically goes like C over L cube. So that's why when you divide the rate for unit flux, 1 over t cancels, and what remains is L squared. And you were talking about M. So what did you mean by M?
Because I think because if I start with, because I've noticed that 1 over h bar, so I expanded 1 over h bar as 1 over the dimension of energy times the dimension of time. And
right, that's
if
right.
I expand energy, then there is an m, and
right.
I don't know did it got canceled.
It didn't get canceled, right? So as you say, I going to F is a matrix element of the Hamiltonian. So the thing inside this square, inside this absolute squared has dimension of energy. And you take the square of this, the whole thing has dimension of energy squared. And delta function of energy has dimension 1 over energy. So that's how everything here has dimension of energy over h bar. That's why this thing has the dimension of 1 per time. And then multiplying that with L cube over C, 1 over time gets canceled. What's left is dimension of the area.
Yes, I got it. Thank you.
You got it? Okay.
Oh,
good.
yeah, there's another question.
Oh, there's another question you said, right?
So I am not completely familiar with the scattering theory, so I don't understand. I don't know the L. What is L? The large L.
L is the size of the box. So we use this box normalization when you actually expand this vector potential in terms of the momentum modes. So inside A, there was a dependence on L for each mode. And that L dependence is supposed to be canceled by this L cube in a factor up front so that physics doesn't depend on the size of the box.
Okay, yeah, makes sense. Thank you.
Okay, all right. Any other questions at this point? You guys should be really happy about this, right? Because now you have this notion that the vector potential is made of creation annihilation operator. So whenever you see A, you can see that is capable of creating a photon, annihilating a photon. And that idea was the essential idea in quantum field theory. And you are now so familiar with this idea that when I tell you that P dot A can create a photon or annihilate a photon, you probably don't feel anything mysterious anymore. So that's huge progress you guys actually made over the course of this semester. That when you see A, you can immediately think of the annihilation creation operator, so that these kind of diagrams would start making sense. So if you feel that this is something you can understand just by drawing these diagrams, that's based on the progress you have made in understanding the idea of the quantum field theory, where a field operator is actually made of creation and annihilation operators. Okay, so now then you can actually use this to start computing it. And the actual computation is in the lecture notes of photons.pdf. I don't go through every step of this because there's just a lot of algebra in it. So I just sketch how things go on the slides today. So this is what you need to compute. And I go through some estimates of how things go. So each of the photon operator inside the expansion of the vector potential has the square root of these factors. And in the end, I annihilate one photon. So I have one square root factor of this. And I also create a photon. I have a square root factor of that. And in the end, everything is now in the absolute squared. So the square roots go. So that's how I get this factor at the end of the day. And what you see here is that you have 1 over omega twice for the initial state and final state. And obviously, initial state photon and final state photon are the same. So omega 1 and omega 2 are the same. So in the end, you have this 1 over omega squared inverse factor. Also, you need to sum over all possible final state photons. And that comes with this the sum over the final state photon momenta, satisfying this delta function. And this photon momenta sum is again given by this integral L cube dq cube over 2 pi h bar cube. And the radial integral for q is cancelled by this delta function because q times speed of light is the energy of the photon. So I'm only left with this the spherical the solid angle integral for the direction of the photon. And so as you can see, the end result goes like q squared and hence omega squared. So that's how the estimates go. And what we like to do now is to estimate this matrix element when the energy of the photon is much smaller compared to the energy difference between the 1s state and 2p state. So that's the low energy photon. And that for the case of the photon we see with our own eyes, the optical photon, that's typically the case. The energy difference between the 1s state and 2p state is in the ultraviolet. It's pretty high energy. That's of the order of the electron volt. And typical photon we can observe with our own eyes is of the order of 0.1 electron volt. So that's why it's much smaller compared to the energy differences among the atomic levels. So in this limit, we say that this is actually in the regime of the Rayleigh scattering. And actually computing this matrix element is pretty complicated. And again, I don't do this on the slide. You can see all the details in lecture notes. But at the end of the day, the matrix element, when you actually sum all of these stuff, turns out to be order omega squared. So if you put all these factors at the end together, so this normalization of the each annihilation creation operator gives you omega 2 minus 2. This sum over all final states photon gives you omega squared. Matrix element is omega squared, and you square that inside this absolute squared. So at the end of the day, if you put all of these things together, you find the cross section goes like omega to the 4th, omega minus 2, omega 2, omega 2 squared, and hence omega to the 4th. And the frequency of the photon, of course, goes like 1 over the wavelength of the photon. So in the end, the cross section goes with 1 over the wavelength of the photon to the 4th power. To compensate the dimension of the wavelength to the 4th, to get the correct dimension for the area, I need to supply something that goes like the length to the 6th power. The only length scales we have in this problem is basically the size of an atom or Bohr radius. So at the end of the day, if you actually go through all of these calculations, you do indeed find something that goes with the Bohr radius to the 6th power. So at the end of the day, the cross section goes like the Bohr radius to the 6th power over the wavelength of the photon by the 4th power. So that's the end result of this calculation. And again, you can see all the details in photons.pdf. I'm not showing all the details, but at least you can see how these dependencies would come about. And when you actually plug in the numbers, for example, for the standard temperature and pressure, which gives you the 22.4 liters per mole. And so you can then understand the density of the atoms in the atomic, the density of atoms in the atmosphere. And then you actually plug in also the this formula for the cross section. You can compute the mean free path of the photon inside the atmosphere. So mean free path is how long a photon can go without hitting an atom. So that goes with 1 over the density times the cross section. So density is 1 of the volume, which you can read off from this standard temperature and pressure expression, times the cross section, which has a dimension of area. So n times sigma has a dimension of 1 over length. 1 over volume times the area has a dimension of 1 over length. And inverse of that gives you the dimension of the length. And that's the mean free path. So whenever you have this, the idea of the scattering cross section, by combining that with the density of the targets, you can estimate the mean free path. So again, this is how long a photon can go without hitting an atom. That's the mean free path. So the idea of the free path is that this is how free a photon is without hitting a target. And that's the path length. And this is the mean average of that. So by plugging in these numbers, where the cross section goes like the Bohr radius, the 6th power over the wavelength to the 4th power, the cross section goes downstairs in the expression of the mean free path. So in the end, you find the result, which is proportional to the wavelength to the 4th power. Here I'm plugging in the wavelength of the order of 4,000 angstroms or 400 nanometers, which is basically the typical the wavelength for a visible light. And if you also plug in this number density coming from the standard temperature and pressure, you just put all the numbers in there, then you find the typical mean free path is of the order of 1 million kilometers. But you can also tell from this expression that the mean free path is quite a bit different between the red light and blue light. So red light has the wavelength of the order of 700 nanometers or 7,000 angstrom. And blue light is what we just looked at, of the order of 4,000 angstrom. The wavelength differ almost by a factor of 2. And raised to the 4th power, this ratio is about 10. So what that means is that red photon has a mean free path that's 10 times longer than the blue photon. In other words, blue photon has 10 times higher probability of getting scattered compared to the red photon. So this is actually a very steep dependence because of the 4th power. And this is something you can understand intuitively. So as we talked about, the way photon interacts with the matter is through this Hamiltonian of EP dot A over 2m. That's the interaction Hamiltonian we used, namely that photon would interact with anything that has a charge, in our case, E for the electron. Photon doesn't interact with anything that doesn't have a charge. So photon doesn't see neutral things. And when you have an atom, which is electrically neutral, the photon does not see an atom. But that's only in the limit of the long wavelength. Once the photon has a short wavelength, then photon can resolve small objects. And then photon can see that what looks like a neutral atom is actually made of the positively charged nucleus and negatively charged electron. And then the photon can scatter off that because now photon sees something electrically charged. So what that means is that in the limit of infinitely long wavelength, photon cannot resolve the structure of an atom. The only thing there is a neutral atom overall, and photon doesn't notice it, and therefore it doesn't get scattered off it. But as you increase the as you make the photon wavelength shorter and shorter, then the photon becomes more and more sensitive to the internal structure of the atom because it can resolve the final structure because of the shorter wavelength. Then it can sense this charged object inside the atom better and better. And as a result, photon gets scattered off an atom for shorter wavelength more and more. So that's how the cross-section increases for the shorter wavelength of the photon. And then how you can see at least this dependence that the cross-section increases for the shorter wavelength because the photon can notice charged objects inside the neutral atoms. So that's how we can intuitively understand this dependence that the cross-section is bigger for a shorter wavelength. And by going through the second order perturbation theory, you can really work things out. As I mentioned, you have these factors on omega from the normalization of the creation annihilation operator, and also the coming from this the phase space integral and the matrix element. By putting them together, indeed, you find the cross section that goes like one of the wavelengths to the fourth power. So this power of 4 is something you have to sit down and compute. But this intuitive argument tells you that indeed the cross section is supposed to go up for the shorter wavelength, and indeed the calculation does support that idea. So that's how you get this the dependence of the Rayleigh scattering cross section, which goes like one over wavelength to the fourth power of the incoming photon. Okay, let me stop here again to see if I have any questions.
I have multiple questions.
Go ahead.
I'm currently looking into the derivations, but I cannot go through it in such a short time. So,
yeah, because I'm not showing it.
I do have, first of all, one question. When I try to understand the yellow equation, I see that there are two terms, which looks very similar to the decay rate, gamma. First of all, why are there two terms? And second of all, when I looked into the notes, the notation of capital A here is also denoted as ground state.
That's right. Yeah, so
notes.
this A is referring to the atom.
Oh, okay. Okay. Okay.
And I is referring to intermediate state. So yes. I guess I had switched the notation from the initial state I to the atomic state A. The final state is also atomic state, so that's A. And instead of using this intermediate state M, I use this notation capital I instead. I don't remember why I did that, but that's what I did.
I have another question.
Go ahead.
Which is, we have the operator of X dot polarization, is it?
Yes.
Yes. I don't understand what this operator is. What does it mean?
Yeah, so this is how it came about from the P over M in the interaction Hamiltonian. And you rewrite P over M as a commutator between X and Hamiltonian at the 0th order. That's a hydrogen atom Hamiltonian. And so the Hamiltonian piece would extract energy differences which is now contained inside this e to the omega to the fourth. And the remaining piece is this x. So that's the same thing, the same trick we used for the calculation of the dipole transition from 2p to 1s.
Oh, so the more physical representation for the operator here should be putting back the omega to the fourth power into the x dot epsilon.
Right, that's right. So the x is originally coming from p. So this is actually p dot a over 2m.
Oh,
So the A contains this polarization vector, and P is now rewritten as the XH commutator, and H acts on the intermediate state in the atomic state, so that is already extracted outside of the absolute squared, and the matrix element keeps track of this X.
I have another question, which is about the denominator. Okay, so this is a combined question because see, we have two terms in here, and the first term we have is the denominator in the first term, and the denominator of the second term differs by plus or minus h bar omega. So what does that essentially mean?
So this intermediate state is when you annihilate the photon first and create a photon later. So the intermediate state doesn't have a photon.
Yes.
So the initial state has atom plus photon, and intermediate state doesn't have a photon. So EI is only the atomic level. So that's the first term, contribution of the first term. Second term creates a photon first, and that's why this epsilon is complex conjugated. This comes with the creation operator. And then you annihilate the photon later. That's why the polarization vector is not complex conjugated, which means that from the initial state of atom plus photon, you create a photon. So intermediate state has two photons. So initial state has energy of the atom plus one photon, h bar omega. But intermediate state has the energy of this intermediate atomic state EI plus two photons, 2h bar omega. That's why energy denominator is EA plus h bar omega minus EI minus 2h bar omega. And that's why in the end, I have minus h bar omega in the energy denominator. So that's the difference between these two terms. If you annihilate the photon and create a photon later, the energy denominator has plus h bar omega, which is the energy of the initial state photon. If I create a photon first and annihilate a photon later, then the intermediate state has two photons, and one of them cancels the energy of the initial state photon, but the other photon energy still remains, so the energy denominator has negative h bar omega, and that's the difference between these two terms. Did I answer your question?
Yes.
Okay, you seem to have one more.
Yes, the last question will be, so we have d omega f. So we only did this, is it because this is a multiple, how do I say this? I scatter through different atoms, which is why I only depend on the final solid angle. Why is it d omega f?
You said different atoms. I don't know what you meant by that.
No,
So
I don't understand why is it the solid angle only the one for the final solid angle?
So the initial state photon has a definite momentum for the problem. So let's say you're talking about the photon coming from the sun. Then the direction of the photon is really coming from the sun. And we are specifying the wavelength of the photon for the purpose of calculation. So some emits the photons of all the possible the wavelength. That's why we see the sun to be white as a combination of all different colors, right? And for each photon, which comes a different wavelength, that's coming from the sun. So we have a definite direction. And what we are doing here is a sum over all final states. And sum of the final states basically corresponds to the sum of the directions of the scattered photon. which is not necessarily in the same direction as the original photon because it gets scattered and goes in the off direction. And you have to sum over all possibilities of the final state photon, and that's the solid angle integral we just talked about.
Yes.
Is that okay?
I think yeah, thank you very
Okay.
much.
Okay, and one more thing, if I actually respond to your set of questions, is that we talked about these two contributions, whether you annihilate the photon first and create a photon later, or you create a photon first and annihilate the photon later. So that's the two contributions I mentioned that gives you two different energy denominators. You may also ask the question, what happened to this contribution of doing the annihilation and creation of photon at once? And you do have to include that contribution in your calculations. And that's still in here in the first line of this slide. But when you actually go through the calculation, and then you actually use this trick of rewriting P over M by the H commutator, it turns out that contributions coming from each of these of the terms with intermediate states actually end up canceling much of the contribution from this simultaneous creation and annihilation of the photon. So after cancellation, this first term is basically gone, and you are left with the two contributions of the different ordering, whether you annihilate a photon first and create a photon later, or you create a photon first and annihilate a photon later. And so these two contributions are there after canceling off the contribution from the first term. So that's why in this yellow expression, it doesn't look like the first term is there, but this is the result of the expression after canceling the first term from the contribution of the two other terms in the expression. That's why you see only two contributions depending on the order of the creation and annihilation, but this already includes the contribution from the first term as well. So again, this is the detail I didn't want to get into because I don't have a big space for slides to show. But when you go to the photons of PDF, you see all the intermediate stages of the calculation in it, how exactly this first term gets canceled by contribution from the two terms of each order in the creation and annihilation. And then after the cancellation, you see these contributions in yellow. And this yellow expression allows you to count the powers in omega very easily. And that's how you end up with this power counting of the lambda to the fourth inverse in the final expression for the cross section. Okay, any other questions here?
Yeah, I have a question.
Go ahead.
Sounds
like you, Chen.
I'm confused by the, yeah, that's me. I'm confused by the explanation that sigma, the sigma goes to 0 as lambda goes infinity, the behavior.
Okay.
I think our Lagrangian only contains the interaction between electron and photons. So
right.
Our theory does not have any neutral atoms in the theory. So I don't think the behavior is because the photon does not see neutral atoms, because we have no neutral atoms in our theory.
So that's a very good question too. Yes, so I did not include the nucleus in the calculation, but the fact that the atoms exist is of course is because of the bound states of electrons and nuclei, and we are using these atomic states for this calculation. So even though it's not explicitly in there, when you talk about atoms scattering a photon, implicitly, so all the electrons are in the bound states together with the nucleus. So in explicit calculations, I didn't have to put in the nucleus explicitly, but in the end, that's actually how the physics works. And the behavior, you can see why the cross-section goes to 0 in the infinite wavelength limit is precisely because of the fact that all the electrons are supposed to be in the bound states together with the nucleus. So you know, that's how the physics goes. Even though I'm not putting that information explicitly in the calculation, then physics actually goes very consistently, and in the end, you see this effect of what we call the screening, namely that in the infinite wavelength limit, all the electrons are supposed to be screening the charge of the nucleus, and as a result, everything is neutral. And more mathematically, the reason why I didn't have to include the contribution of a nucleus is that even if I try to put the nucleus in there, then the contribution of the photon scattering by a nucleus goes like EP dot A over 2m, where m is the mass of the nucleus, and which is way bigger than the mass of the electron. So the contribution of the photon interacting with the nucleus is way suppressed compared to the interaction with the electron. And what we have done is basically treat the atom as infinitely heavy for the purpose of this calculation, which is the same thing as sending the mass of the nucleus to infinite. And that's why we can treat the atom as a static object without thinking about the recoil in a scattering of the, when it scatters a photon. And infinite nucleus limit is mathematically the same thing as putting in the contribution of the nucleus in interaction Hamiltonian, which is 0 in the same limit. And that's why without putting the nucleus in the explicit calculation, it takes care of this infinite heavy nucleus automatically. Does that answer your question, Yu Chen?
Yes.
Okay, good. Any other questions? Okay, so you can ask questions about this after seeing the next slide, because that's where this dependence becomes crucial. And I would think that you probably know this story already, but anyway, this is the reason why the sky is blue and the sunset is orange. So when light comes from the sun, and if you look directly at the sun, of course you shouldn't, because that would burn your retina. But anyway, then you can see the sun itself. But when you see the off direction in the sky, then you see the sky blue. And obviously, when you look at the sky, you are not looking into the sun. You are looking at an off direction, but you see light, blue light coming into your eyes because that's a scattered light. So sun would go to the come towards our planet, and the light would hit atom in the atmosphere and get scattered and into off direction. So when you're looking at the sky, you're not looking into the sun, you're looking at off direction, but you still see light coming into your eyes because that's a scattered light. So light comes from the sun, hits an atom in the atmosphere, and the direction of the light changes. And that's why it can go into off direction now into your eyes. And as we talked about, the blue light has much higher probability of getting scattered. So the light you see after the result of scattering is dominated by the blue light, and that's why the sky looks blue. On the other hand, when you look at the sunset, which is the great thing you can do here in the West Coast, because the sun sets in the west, and you can see the beautiful sunset, and the light goes through the atmosphere for a very long path, because the sun is near to the horizon, then it has to go through the atmosphere for a long path in the atmosphere. And in the course of the light going through the atmosphere, the blue light gets scattered away. And therefore, the sun, when you look into the sun near the horizon, pretty much all the blue light gets scattered away on its path. And what remains is the red component. So that's why the sunlight is dominated by the red component, because you have removed the blue component by the scattering. And that's why the sun looks orange at the time of the sunset. So this dependence we saw on the previous slide, namely that the cross-section goes like one of the wavelengths to the fourth power, is the reason why the blue light gets scattered more than the red light by almost a factor of 10 on an order of magnitude higher probability. And the fact that the mean free path for the blue light is about 1,000,000 kilometers means you can still get the blue light even at the time of the sunset. So because the radius of a planet is of the order of about 6,000 kilometers, and mean free path is longer than that. So the good news from this number that you can see the sun even at the time of the sunset. But it's also is a case that the red light gets scattered much less than blue light by an order of magnitude. So you retain a lot more red light coming from the sun at the time of the sunset compared to blue light. And that's why the sun looks redder. So that's how we understand why the sky is blue and why is the sunset orange, using this dependence of the Rayleigh scattering cross section that goes like 1 over wavelength to the 4th power. And as you all know, that the sun is made of the entire spectrum from the black body radiation on the surface from the temperature of about 6,000 degrees. That's why sun as a whole looks white, containing this entire range from the violet to red. And the combination of all of them, that's what we perceive as a white light. And that's because we see 3 different filters in our retina for red, green, and blue. And so this actually shows the wavelength ranges that can be captured by our retina for the red and blue and green pigments. And if you see all of them actually coming together, that's why our brain thinks that we are looking at the white light. But with this idea of the light gets scattered, then you actually see the rest of the contribution of the blue at the time of sunset. And then it gets dominated by this red component. And that's why our brain thinks that we are looking at something red or orange. On the other hand, when you look into the sky instead, the red components are not scattered very much. So the light is dominated by this blue component. And that's why our brain tells us that we are looking at the blue sky. And of course, the sunlight is not exactly the black body radiation because of the absorption of light by the atoms on the surface of the sun, as well as absorption of light in our atmosphere too. So it's not quite this beautiful black body radiation curve in yellow. So what we see is a result of these absorptions. So it's shown in this black. So it's not quite black body radiation, but in this visible photon wavelength, it retains pretty much the form of the black body radiation. So it's still a good approximation. So out of this black body radiation curve, what we see is in these 3 filters of the pigments in the retina, red, green, and blue, and depending on the ratio of the light energy in this red, green, and blue components, we perceive the light being red or blue or various other colors. So the only thing that matters in a perception is the ratio between these 3 filters. And based on that ratio, we perceive a particular color of the objects we are looking at. And in the case of the sky, the light from the sky, because the blue component is dominating over the red component from this Rayleigh scattering cross section, we think the sky is blue, even though there's still red light. What matters is the ratio. Again, if you're looking at the sunset, the blue light gets scattered away, even though there's still blue component. In terms of ratio, red light dominates. And the ratio is the only thing that matters for perception of color, and that's why the sun looks red. And so that's something I'm sure you have heard in freshman physics class, but now you know quantitatively how this calculations comes about in terms of how light gets scattered off a neutral atom and is dominated by the blue component by almost an order of magnitude because of the dependence of one of the wavelengths of the 4th power. And then that translates into this discussion, why the sky is blue and why is the sunset red. Okay, let me stop here again to see if you have any questions.
I do.
Okay, go ahead.
First of all, this is very cool because like we have never done this in Italy. So thank you so much for like for this curiosity that I didn't know.
Is
And
this
second of all,
I don't
Yeah,
see
it's me.
picture. Okay,
Yeah,
good.
sorry. Yeah, it's me. And second of all, I have a curiosity, which is all of these, like all this theory of scattering and all the free Feynman diagrams that we saw were about the second order, the first or the second order perturbation theory. And my curiosity would be like, how do the diagrams of like a third order perturbation theory looks like?
Oh, it's the same idea. So initial state comes in, you have some interaction Hamiltonian, you go to the first intermediate state, and you interact with another interaction Hamiltonian, you go to the second intermediate state, and you have interaction with the third interaction Hamiltonian that will take you to the final state. So instead of drawing one line for the intermediate state, you draw one line, one block, and another line before hitting the third interaction Hamiltonian going to the final state. And for each intermediate lines, you associate this energy denominator. So just by drawing the diagram like that one, you don't need to go through this calculation of time-dependent perturbation theory and integrating over time. You immediately can write IVM1, M1 VM2, M2 VF as a product of three matrix elements. And you have two energy denominators, EI minus EM1 and EI minus EM2, and that's the contribution to the matrix element. So drawing diagram like this one is a very useful way of remembering how to work out the matrix element without going back to this whole business of interaction picture and time evolution operator. You just go ahead and write this amplitude right away. So that's the idea.
I see, because like I was wondering, like if we add a vertex in the middle of the interaction line, then we need that the vertex is both an annihilation and a creation place, right? Because otherwise we don't have like the right number of photons.
Right.
Okay, so it's okay. This is okay. Good.
So
Thank you.
if you are interested in a question like what happens when you send in one photon, and you would like to see two photons coming out as a result of scattering, which is very much suppressed by 2 extra powers of alpha. So you don't see this in typical experiments, but it can happen. So in that case, you can compute the process like the first interaction Hamiltonian annihilating the photon coming in. You go over to intermediate state. You hit the second interaction Hamiltonian to emit the first photon for the final state. You go to another intermediate state and hit the third interaction Hamiltonian to emit the second final state photon to go to the final state of the atom. So that's how you can use the third order perturbation theory to compute the process of photon hitting an atom and to produce 2 photons in the final state. That's one example what you can compute as a third order in perturbation theory. Are you happy, Alessandro?
Yes, absolutely. Thank you so much.
Okay, good. Any other questions about this whole discussion on the Rayleigh scattering and why the sky is blue and why is the sunset orange? I'm just going through all these animations now. Right. So that's the sunset. By the way, so when you actually look at a TV or computer screen, of course, they are made of these 3 pixels of the red, green, and blue, and that's RGB for the dealing with the colors on computer. So the actual light emitted from the computer screen is very, very different from the light coming from, for example, the actual sunset, right? So the only thing that the computer screen is capable of is giving the right ratio between red, green, and blue. So it actually doesn't resemble anything remotely as the original, the color of the sunlight from the sunset. The only information that is reproduced correctly on a computer screen is just the ratio between R, G, and B. So if you have some other animals which have more filters in the retina than we do, and I don't know if there's such an animal on our planet, or maybe on a different planet, and look at our computer screen, and they would think what they see on a computer screen is totally different from the actual image of the sunset. So the only thing we see on the computer screen is this correct ratio between R, G, and B, So we are being fooled, actually, by the computer that we think we are looking at a picture of the sunset, but the actual color of the light coming from the computer screen is just totally different from the actual color of the light from the sunset. The only thing that's correct is the ratio of R, G, and blue, as I said already. So we are all being fooled by looking at the picture on a computer screen. So that's something which is sort of humbling, that we are being fooled by this TV and the computer screen the every day. We think it's accurate representation of the color, but it's actually not. It's thanks to the limitation of vision that the computer can represent what looks like authentic color, which we can see on the screen, but it's actually not. Right. Any further questions about the Rayleigh scattering? Looks like people are happy. So now I come back to the question of this I epsilon. So when we talked about this I epsilon as a mathematical trick to make sure that the time integral in time-dependent perturbation theory converges, I told you that this I epsilon is something I will come back and talk about later, because that is the way we can avoid cross-section becoming infinite. So idea here is that, we talked about Rayleigh scattering, where the energy of the photon was much, much less than the splitting among the atomic states. That was the limit when we estimated the Rayleigh scattering cross-section. But in principle, you can send in a UV light where the energy of the incoming photon is precisely the energy difference between 1s and 2s state of the hydrogen atom. Then you might think that this energy denominator is 0 because EI is the energy of the 1s state plus the photon. EM in this sum can correspond to, for example, 2p state of the photon, the atom. And if the energy of the photon is such that corresponds to the energy difference between 1s and 2p state, EI, the sum of 1s plus photon, and EM, the 2p, can be exactly the same as with each other. Then the energy denominator vanishes. So then you have only one I epsilon, which is meant to be infinitesimal. So the cross-section diverges. But of course, in physics, nothing should be divergent. Cross-section has to be finite. And so what's going on in that case is that photon coming in would excite 1s state to 2p state. What was supposed to be the intermediate state, where you borrow energy within the uncertainty principle, is not a borrowing energy anymore, because it really does become 2p state. So in the Rayleigh scattering, where the energy of the photon is much less than the energy of these excited states, you did have to borrow energy to go to the intermediate states of 2p, 3p, 4p states, because initial state doesn't have enough energy to really become 2p, 3p, 4p states. In that case, you say the intermediate state is a virtual state because it's not real. But when the energy of photon corresponds precisely to the energy difference between 1s and 2p, it's no longer virtual. It is a real intermediate state. You can really excite 1s state to the 2p state. But one thing we also know is something we have computed already, that 2p state doesn't live long enough. It would eventually decay. So it turns out that when you actually compute the correction to the energy of the 2p state, it acquires an imaginary part, which corresponds to the decay rate of the 2p state. So what I'm actually going to show you now is that you are supposed to stick in this imaginary part to the energy of the 2p state, because it's not a stable state. It is a state that decays. A decaying state has the energy which contains the imaginary part. So when you actually stick in this energy denominator for the 2p state, energy of the 2p state is no longer real, but contains this imaginary part in it. And this imaginary part corresponds to the decay rate of the 2p state. So even if you send in the energy, the photon, whose energy is precisely the energy difference between 1s and 2p, energy denominator doesn't vanish because of this imaginary part of the energy of the 2p state, and the cross-section remains finite. So what I'm going to tell you in the next couple of slides is why the 2p state acquires this imaginary part to its energy. And you might think that's actually crazy, because we get told in quantum mechanics class that the energy is an eigenvalue of the Hamiltonian. Hamiltonian is a Hermitian operator. Any eigenvalue of a Hermitian operator is real. Hence, the energy eigenvalue has to be real. But here I'm telling you something different. Energy of the 2p state is not real because it decays. It has the imaginary part to the energy eigenvalue. So I will try to tell you in the next few slides why that is not a contradiction, why you expect the energy of the 2p state to have an imaginary part, contrary to what you get told in quantum mechanics class. And that's the way you see consistency, namely the cross-section doesn't diverge and stays finite. So that's where my discussion is going now. So I epsilon, which was a mathematical trick, is now getting promoted to I finite number, not infinitesimal. And that finite number ends up corresponding to the decay rate of the intermediate state. So obviously, I'm not finishing discussion here. I'm just giving you an upshot where I'm going. But do you have any questions about where I'm going? Okay, so I'm sure you have more questions to ask when I get to the actual discussion. So idea here is the photon comes in, and that can excite the 1s state to 2p state as a real intermediate state, where you don't have to borrow energy when the energy of the photon precisely corresponds to the energy difference between 1s and 2p states. So let's look at this energy denominator with this imaginary part in it. So again, if you go back to the second order perturbation theory you have done in quantum mechanics, I'm sure you have seen an expression like this one. Energy gets a correction at the second order perturbation theory with the energy denominator, EI minus E, intermediate I, capital I, and the numerator is the matrix element of the initial state going through the interaction to the intermediate state, and intermediate going back to the initial state by the interaction. So this is the expression you learn in quantum mechanics class, how much energy gets shifted at the second order perturbation theory. And the difference we have now in the QFT is that this intermediate state is a continuum, because it can have continuous possibilities of all the energy of the photons. And that's why this EI over E capital I can in principle be zero, and that's something we are worried about now. And what the reason why we went to the second order perturbation theory in gory detail in deriving the expression is that we were supposed to put in this I epsilon here to make sure that every integral converges. So we keep this I epsilon for the purpose of discussion. But once you have this I epsilon here, this is something you learn in complex analysis. This expression of 1 over x plus I epsilon tells you how your integral should avoid the pole. So here you have a pole when x is negative I epsilon. So when you are integrating over the real axis for the variable x, the pole is at minus I epsilon. So that is supposed to be slightly below the real axis. So if you remove this I epsilon, you don't know how to deal with the pole. You exactly go through the pole, and you might encounter infinity, and that's when you have a problem. But keeping I epsilon in here, you know how you go around the pole to avoid infinity. Namely, the pole is supposed to be slightly below the real axis. So your integral contour goes above the pole. So keeping I epsilon in your denominator is telling you that you are supposed to avoid the pole by going above it, not below it or through it. And this is a formula you learn in complex analysis. So one piece corresponds to this line before getting to the pole, and another piece after passing the pole. So adding this piece on the left and this piece on the right is something called the principal value integral. On the other hand, piece going around the pole is the same thing as the halfway of going circling around the pole. When you circle around the pole, that's a residue integral, where you actually take the pole and evaluate the residue at the pole. Namely, that's the contribution that corresponds to the delta function of evaluating the rest of the integrand, except for the pole factor, evaluated at the pole, namely that's a delta function. And when you encircle the pole clockwise, that gives you a factor of minus 2 pi I. When you avoid the pole, that's a semicircle, you get a contribution the half of that. So you get a contribution of negative pi I instead of 2 pi I. So that's the formula you learn in this expression. So namely that once you see a pole with this plus I epsilon in it, there are two contributions to the integral. One of them is this principal value integral, where you do the integral except for the pole. And the other contribution is the half the residue integral because of the semicircle around the pole. And there's a definite sign for it. If the pole is avoided with negative I epsilon in the denominator, then that means the pole is above your axis, namely that you are going below the pole. Then the contribution would be counterclockwise. And then the sign of delta function is plus I pi. So the sign of I epsilon is actually important because that is telling you whether you're supposed to go above the pole, which is the case we have, instead of the below the pole, that's the case we don't have. And now that we know you're supposed to go above the pole, that definitely fixes the sign of this delta function. So if you look at this expression for the second order energy shift in perturbation theory, the fact that we have this I epsilon, which you haven't seen in quantum mechanics class, but now you do see in a second order perturbation theory in QFT, you know which sign of the delta function you are getting. So if you take the imaginary part of this expression for the second order energy shift, imaginary part of delta E has a piece coming from this delta function with a definite sign of the negative I pi. And when you actually take this delta function, the EI and E capital I are the same. That's this delta function over here. And the residue is what's in the numerator. That's the absolute square of this matrix element squared. And now if you remember the expression from the Fermi's golden rule, this matrix element squared times the delta function is nothing but the decay rate times h bar. But this is 2 pi I, no, this is not 2 pi I, but pi I. So this is actually a factor of a half in there. So as a result, from this expression for the second order perturbation theory, you draw the conclusion that the imaginary part of the energy shift is negative. And that's a sign which makes sense, because when you have the energy of the 2p state now acquiring a complex energy with this imaginary part being negative, then the time dependence of the energy eigenstate is e to the minus I et over h bar. But energy now has this imaginary part in it. And this energy, the imaginary part of the energy, when you actually compute the probability of this, without the imaginary part, probability is 1, namely that's a stable state. Once you have the energy eigenvalue and energy eigenstate, it's a stationary state which always is in that energy eigenstate forever, and that means the probability is 1. But once the energy has acquired this imaginary part, that's no longer the case now because of the time dependence of the real amplitude. And by squaring it, you cancel this factor over half in the imaginary part. So that becomes e to the minus gamma t over h bar. And that's indeed the exponential decay law by identifying h bar over gamma being the lifetime of the state. So the state acquiring this imaginary part in its energy actually makes sense because that precisely corresponds to the situation where state decays exponentially. Imaginary part of the energy is precisely the decay rate over 2. So having imaginary part of the energy is actually not crazy because that is telling you that the state is no longer stable. It's stationary state in the sense that there's an eigenstate of energy, but not quite stationary in the sense that it decays. And how quickly it decays really corresponds to the imaginary part of the energy eigenvalue, which you can compute due to the second order perturbation theory, thanks to this I epsilon. And if you have opposite sign of I epsilon, you find this crazy result that the state of the probability would increase exponentially. And that's really crazy. That shouldn't happen. So the fact that we retain this I epsilon with the correct sign from the second order perturbation theory guarantees that state can only decay exponentially, not increase exponentially. So having retained this Y epsilon piece from this integral, which you performed for the second order perturbation theory, really did have an important meaning that energy now acquires a slight imaginary part to it. And sign of the imaginary part is the correct sign, namely that will lead to exponential decay of the unstable 2p state as an example. So when you actually do the scattering of the photon, when the energy of the photon precisely corresponds to the energy difference between 1s to 2p state, then it's true, it does lead to the real intermediate state instead of virtual intermediate state, because you don't have to borrow energy. It really does become 2p state. But it doesn't lead to infinite cross-section, despite the fact that EI minus EM vanishes, because the 2p state now has acquired this imaginary part to its energy. So EM is no longer real. It has this imaginary part to it. And then the energy denominator cannot exactly vanish, thanks to this imaginary part, so that your cross-section remains finite. And the way the 2p state energy acquires this imaginary part is what I explained over here. So this expression for the energy shift at the second order perturbation theory also has this I epsilon in it. And that I epsilon dictates how you can compute the imaginary part of the energy. There's no ambiguity. And just by complex analysis tells you that this energy denominator contains this delta function in it. And that delta function gives you the correct sign for the imaginary part of the energy that corresponds to the exponential decay law. So when I told you the Fermi's golden rule tells you what the lifetime of the state is, I waved my hands and came up with this explanation. But now you see directly that it is really the imaginary part of the energy, and that's how you directly derive this exponential decay law without waving any hands. This is now the consequence of the second order perturbation theory, which does lead to this imaginary part of the energy. When you stick in this imaginary part of the energy, this exponential decay law comes out without waving hands. And that's how we can identify the inverse of the decay rate being the lifetime of the state in the form of this exponential decay law. So that's how this I epsilon turns out to be important in perturbation theory to correctly describe how the unstable states decay exponentially as an end result of the imaginary part of the energy eigenvalue. Okay, so that was a long discussion, but let me stop here to see if you have any questions. I'm sure there are. By the way, are you familiar with this formula from the complex analysis? that 1 over x plus I epsilon is the sum of the principal value integrals for the sidebands for the left and right components, avoiding the pole, and this minus I pi delta function, which corresponds to a semicircle of avoiding the pole above. Have you seen this before?
I've heard about pole and learned about it, but I'm not sure that
I see, but so you have heard about avoiding the pole, but you haven't seen this expression written down.
For me, no.
Okay, is that the case with the other people too? I'm not hearing anything. I even don't know if anybody's there. I see the 21st. I see some chats. Let me open that. I have not. I've seen it. I haven't seen it exactly in this form, and so on and so forth. Okay. All right. So I also see some people left because of another class. I don't know why there's a class at this moment, but anyway. Oh yeah, that's right. So I went overtime. I apologize. So sorry. So then let me stop here and let's see if I have anything else that should be added. Oh yeah. So the last thing I wanted to mention now that I'm over time is that this energy denominator with this complex energy is what actually gives you the cross section of this behavior called the Lorentzian. So if you look at the behavior of the cross section for the energy close to the energy difference between 1s and 2p state, when you exactly hit it, then EI and EM is 0. So cross section goes like 1 over gamma squared. That's the peak here. When you're slightly off, this almost vanishes, but not quite. And the absolute square of that is given by this expression by taking the absolute square of the complex number in the denominator. That will give you this behavior as a function of energy. Meaning that even if you are slightly off from precisely the energy difference between 1s and 2p, you still have the enhancement in the cross section with some width. And this gamma, you computed the Fermi's golden rule on the previous slide, correspond to the width of this peak at the full width half maximum. Namely, compared to this, the peak of the compared to peak, half maximum means half the peak size, and you're looking at the full width at the half maximum. That's full width half maximum, and gamma has the meaning of the width. How much you can miss the energy, but you still see this enhanced cross section. So we call this gamma often at the width of the state. So energy, of course, is the energy of the state 2p, but 2p state also has the width, and the width corresponds to the inverse the lifetime. And when you actually see this resonance scattering, you say that this is a resonance because you see this enhancement when the energy corresponds to the energy of the 2p state. But even if you slightly miss it, the 2p state has broadened by this width, and you see this enhanced cross section. And so I'm going to repeat this discussion on Wednesday, and I am sure I can be back in person to teach on Wednesday. Now that I went over time, I have to repeat some of the discussion I had, and I apologize for that. But let me finish up this discussion on Wednesday. So the width of gamma has the meaning of really the width of the 2p state energy, which corresponds to the inverse lifetime. And that's another manifestation of energy time uncertainty principle, namely that when the state has the finite lifetime, delta t is finite. Correspondingly, delta E is also finite. Namely, the energy of the 2p state is a little bit uncertain, and that uncertainty is given by gamma, which corresponds to the inverse of the lifetime. So everything makes sense at the end of the day. Okay, so let me stop here. And if you have any further questions, please ask.
Actually, I have a question.
Go ahead.
I'm not very clear that how does the complex energy of the intermediate state enters our discussion of the second order time-dependent perturbation theory, because in the discussion, what we do is to compute the eigenvalue of the Hamiltonian on the intermediate state, and clearly this kind of imaginary energy comes from perturbation. So we can that is not contained in our actual or the naive energy denominator. Then how does it comes in the denominator?
Yeah. So when you actually do the second order perturbation theory for the cross section, you need to stick in the energy of the intermediate state. So energy of the intermediate state is supposed to be the eigenvalue of the unproved Hamiltonian, which you work out separately. And once you know the energy eigenvalues of Hamiltonian, you stick that into this expression for the cross section. But when you actually work out the energy of this the intermediate state on the side to plug that into this expression, you also have to do the perturbation theory to compute the energy levels as well. And when you compute the perturbative correction to the energy of the 2p state, you have to compute this quantity, where initial state is 2p now, intermediate state is 1s state plus a photon, going back to 2p state. And that matrix element can have this EI minus E capital I vanishing. That's why you have to take care of this pole using this prescription that gives you this imaginary part of the energy of the 2p state. So you work this out on the side, and then you plug that into this expression for the cross section. So that's how you can compute everything self-consistently. So immediately working up, oh, go ahead.
Is that something similar to the concept of self-energy in the covariant perturbation theory?
That's exactly right. So if you go to Lorentz invariant QFT, which we will do after maybe one lecture, then this contribution is precisely what is called the self-energy. So namely that if you have particle, which is unstable, then you go through this calculation to compute the correction to the mass of the state. And mass is the energy because it's E equal mc squared. And then you also find the imaginary part to the energy of the particle or mass of the particle. And talking about imaginary part of the mass sounds very crazy, but nonetheless, it's the same idea that you do find imaginary part to the mass of, for example, the W boson in a wake interaction. And that's an unstable particle. So it decays, and decaying unstable particle means its mass has imaginary part to it. And then you stick in the energy together with the imaginary part to the computation of the cross section. When you, for example, compute the cross section of the collider experiments producing W boson.
Okay, so basically, can I understand this this kind of imaginary energy as summing all the intermediate, all the higher order perturbation that have the same intermediate state? Like
that's right.
Yeah. Okay. Thank you.
Okay. Any other questions?
Yeah. Like, hi, Professor. I'm also a bit confused by that gamma thing because, like, how we get the energy denominator in second order perturbation theory is basically like we have the unperturbed Hamiltonian on the exponential, and then we like attain a eigenvalue from the intermediate state, and then perform the integration to get the denominator. But yeah, in that case,
so that's a good question. And so the diagrammatically, what you're doing is the following. So take this diagram over here. So initial state is 1s plus photon. And then that can hit this 2p state when the energy of the photon is exactly right. But this 2p state can also have the high order perturbation theory, where you have this interaction of Hamiltonian going to 2p state. 2p state would hit another interaction Hamiltonian to go into oneness state in a photon. And this photon comes back with another interaction Hamiltonian back to 2p state. So that's a high order correction to this cross section we talked about. And normally that's suppressed and you don't need to worry too much about it. But when energy of the photon is very close to excite the energy of the oneness state to 2p state, that small correction becomes important. So you have to include it. And you have to include it multiple times. So 2p state can have the interaction emitting a photon and reabsorb it to become the 2p state again. And you can do it once again, emitting a photon, absorbing it. And in principle, you have to do this infinite times. And if you sum them up, and that correction, summing up, would sum up in a geometric series, and that correction precisely appears downstairs into this energy denominator. So this energy denominator with this I gamma in it is a result of summing over the infinite times of emitting a photon and reabsorbing it in this propagator of the intermediate 2p state. So diagrammatically, you are summing over all the infinite number of diagrams to obtain this correction to the energy denominator. Sorry, Ryan.
Okay, so you mean that there's something that we like kind of there are some terms that is suppressed in the derivation of second order perturbation theory that cause the I gamma becomes like I epsilon in that expression. So the proper way to restore it is because the problem is that I didn't see any point that we like kind of like ignore some terms in our derivation, and so it seems like the result
that's because,
of that.
Right. So far we talked about only the lowest order perturbation theory. So for the scattering process of photon of an atom, these contributions are sufficient at the lowest order perturbation theory. But when the energy of the photon is close to hitting this resonance, this becomes so small that you have to go beyond the lowest order perturbation theory to make sense of the cross-section. In high order pieces is precisely what I mentioned, namely that this intermediate state 2p can emit a photon and reabsorb it. Emit the photon and reabsorb it multiple times on its way. And because it's quantum mechanics, you have to sum over all amplitudes for the same initial state and final state.
So like the geometric series would give you
this
that correction down to the denominator. Okay,
exactly. Right.
That makes sense. Thank you.
Okay, good. Any other questions? Even though we're way over time now. Okay, go ahead.
I said I don't have any.
Okay, good. Nobody else? Okay.
By the way,
so sorry for going over time.
Do we have an office hour today?
Yeah, again online, but we have an office hour. Yes.
Okay. Okay.
See you later.
Thank you.